Okay, the recording is on. So, good morning once again. My name is Andy Baresi Shigota, and I am going to be holding this class lectures for this class, in addition with Professor Zlatan Car, who will join us in later classes. So, this class is practical data collection. What we will aim to do here is to essentially cover the basics of how to collect data, what kind of things you should pay attention to when collecting data. We are talking about a pretty general overview of when we are talking about data. So we aren't going into practical elements of how to connect a specific type of a machine to a computer or something like that, but just covering the general principles that no matter what field you are in, you have to kind of understand and know. And today we are going to go over why is this important, basically what's important about practical data collection, and we are going to cover some basic statistical approaches to checking your data and understanding your data, so we can, just as a basic for going forward in discussions. In addition to this, I will just note that at the end of this class, to pass the class, it's not just attendance. You will have a very short seminar to write, which will essentially, a two-page seminar that will describe basically you will pick some sort of data collection method or principle, and you will need to just write about it and say what would you do, how would you check if it's fine, just a page or two as a short seminar or an exam. We will discuss this at the end of the lectures, the final class. We will go over this in bigger detail, and I will send more details to you and to people who aren't here via email that you used to sign up, so you don't have to worry about that. Okay, so let's start. These are the topics we're going to cover today. I said this. There is an error. It should be topic 1 is expert knowledge. We're going to discuss about what is expert knowledge, what expert knowledge means, and why is it important. How you can track the data visibility being collected. Then we're going to talk a bit more in detail about data redundancy. We covered this in we covered the basics of data redundancy in data storage and management mandatory class. But we will discuss some specifics about how to, when we are talking about actual data that we are actively collecting, how to achieve redundancy there. And finally, we're going to discuss about ethics and regulations. And in the final class, we're going to go through certain discussion of examples where either I or Professor Zlatan will be able to present some of the examples that we had through the years, essentially maybe show you some papers that we published to tell you about some problems that we encountered through years of experience working with machine learning in practical applications. And we'll go over that task that you have a short design of the experiment that I mentioned. Okay, so let's talk about the first topic today, which is essentially expert knowledge, and what it means in context of data collection. So let me just mention, if you have any questions or a comment or anything, feel free to just turn on your mic and talk, or raise your hand, or write in the chat. I personally, I don't mind interruptions if you want to ask questions or add something, so go ahead. So let's talk about, what is expert knowledge. So this class is essentially designed for two groups of people. We have people here who are, computer scientists, computer engineers, who don't have expert knowledge in certain areas. We're talking about medicine, right? For example, and people who are from those specific fields that have the expert knowledge, but don't necessarily know information about the data. So it's designed to basically cater to both of you, and to help understand and see things from both perspectives, because my experience is that going back, I've had issues with people who are experts not understanding, being like, oh, it's simple, it's just data, don't worry about it, and that can cause issues going forward. So whenever you're collecting data, that's what we're talking about here. You want to do it, you don't want to do it on your own unless you have experience with a certain field. For example, I am I'm working with machine learning, but I am also, I would call myself an expert with quotation marks in robotics. I know how robots operate, how to collect data, how to connect to it, etc. So in that sort of a case, I can do it on my own. I can collect data on my own, right? But for certain things, for example, medicine, I may want to have someone next to me, right, who is a medical expert. So when we are going over, for example, X-rays, to me, all X-rays are the same. As long as they aren't overly blurry or corrupted, it's okay. But for example, a medical expert might recognize, oh no, this X-ray of a knee isn't showing us the proper rotation that we need to, or isn't showing us this particular bone that we want to examine, etc., which I wouldn't notice by myself at first. So that's where we need, expert knowledge, because they can recognize the simplest example is, if you're measuring something and you get an out of range error, will you recognize that? Hey, for example, we all know that if we're measuring patient temperature, we know that, okay, if we get 70 degrees Celsius, that's very probably an error, because a person can survive having their internal temperature that high. But if I ask you, okay, what's the operating range of a turbine, of a steam turbine? I don't know that, probably, despite, having worked with a lot of data specific to steam turbines, because one of my colleagues here deals with that, and I worked on a couple of researchers in that with him. I don't know what the proper operating range is. Why? Because he's the expert, and he checks the data that gets collected, and he can tell me like, okay, hey, there's an error here. We collected the data wrong. So that's one of the elements of why the data why you need an expert here. Another is defining data requirements. So you don't necessarily, as a non-expert, know what is important, what isn't. Basically, this is the second point is key here. Expert needs to provide you context. You can collect a ton of data, right? And usually, one of the rules of the thumb when you're collecting data on your own is collect absolutely everything that you can. And in general, it's better to have more data collected than not, but that's not always the case in all examples, because data collection can be expensive sometimes. What I mean by expensive isn't necessarily cost, like financial. It can be that as well, but it can be time. So, for example, in medical data, right? Do we need to have a CT, computer tomography, or a magnetograph scan for everything? No, maybe an X-ray is enough. Maybe just certain measurements, that can be more easily collected are enough. And for example, this is important because a CT or computer tomography might have a longer waiting list than an X-ray. So we can collect data for many more patients using X-rays if X-ray provides us all the information that we need compared to CT. And how will we know if X-ray is enough? Well, I don't, but sitting down and asking an expert in medicine, I'm asking, hey, if we are trying to classify whether the person has pneumonia or not, can we do that with just an X-ray? And they will probably say, yes, you can just do it with an X-ray. You don't need CT for that. And that means that I can collect data much faster, and not only much faster, but that data has less size. CT scans are bigger than X-ray images, so it's faster for me to actually develop a model with that, and that's something that can be key. In other cases, maybe that X-ray isn't enough. Maybe we are trying to segment for a position of a tumor in a chest, and that can be done with just an X-ray, and that. But maybe me, as a computer engineer, I might say like, oh, hey, we can just do it with an X-ray. We're going to assume that it's circular, spherical, and just extrapolate for that. While the medical experts will say, no, you can just assume things like that. That's not always the case. There are a lot of examples where it might not be spherical. It might have an irregular shape, and we need to do a full CT with slices to approximate the shape. So that's something that will essentially give you expert will give you the scope of what data is important, what data isn't important. And while in some cases it's fine to just say I will collect everything, it's not always the case, because again, there is a cost associated with data collection, and that cost isn't necessarily negligible. And the final point here is, ensure alignment between data collected and the goals of the analysis or study. This is something that happened to us, where we essentially collected when we target something that's not important. We're going to talk about that when we come to examples. The second thing is, expertise in designing data collection. So, for example, we know, right, we will talk even today how to check that data we are collecting is statistically valid, but we can say if it's valid domain-wise. What this means is essentially that there are good ways to collect data and bad ways to collect data. With bad ways to collect data, you can introduce noise. One of the example of this is service. There was a lot of discussion whenever there is like a test, a blind test in for any test. There was recently, if you're following like Mr. Beast chocolate that was published, they had like a blind test that was performed, and it showed like, oh, out of 100 people, most preferred our chocolate. While some other YouTubers and other, basically statisticians and food scientists said, oh, that's not how you perform a blind test, because you can very easily manipulate blind test despite it being blind, and you can do the same with any blind test. So, for example, one blind test that you can easily manipulate is if you are comparing audio quality across different headphones, by just saying, oh, it's all fair because we're using the same source, and we're using we're using the same source, we're using the same order for everyone. That's not necessarily good. Why? Because if I give you really bad headphones at the start with the same audio source, right? I give you really bad headphones at the start, and you will be like, oh, this is really bad. Then I give you mediocre headphones. You will feel a big jump in between quality. You will say, oh, these headphones are great. Then I give you really good headphones. You will feel a smaller jump and say, oh, these are better, but the improvement isn't as much. Maybe I actually prefer. You will analyze it more because you're comparing something good to something good instead of something good to something bad, where you're automatically deciding, oh, this is good, right? This is nice. And because you have automatically decided that your first impression of the headphones, right, of the second mediocre, let's call them headphones, was that they are great compared to the previous element that you were grounded in, that was your first impression, they're good. For the second headphones, your impression probably wasn't, oh, they are good. It was, oh, they are similar, I don't know. So just because you had that great first impression, you actually are more likely to vote for that second headphone, despite the fact that they aren't as good. And that's one of the examples how you can manipulate blind test, not test, but any blind test. So we need to shuffle the testing order, etc. So there are a lot of examples that exist, and there are a lot of these types of biases that exist in different fields. How are you collecting? Can you collect data for someone that is sick? For example, we talked about medicine before. If you're collecting data while that person has some sort of infection, and you want to determine whether they are, whether their core temperature influences is an indicator or not. Well, that's a problem if they have at the same time that they have a tumor or something, a cancer, they have an infection. So that's something that you need to check in addition to the actual, testing, etc. So that's something that you need to sit down with experts and discuss and say like, hey, this is our goal. How can we, develop the actual methodology to collect this? Uh, the second, the third thing with expert knowledge is data sources identification. So we're talking about where we are getting the data from. Uh, there are, if you type in dataset in Google, you will get hundreds of sources. Not all the sources are reliable, but to an outsider, something posted on a random website compared to something posted on, for example, data sets that I usually require from UCI, University of for Computing in Irvine. This is the show the website. Just a second. So this is, for example, one of the locations where I get my data sets if I'm looking for an open data set. You see Irvine Machine Learning repository. We're here because this is curated data. You see that they have 670 data sets, right? They don't have thousands or millions. That's because they specifically check the data sets before they are uploaded, make sure that they're good quality, etc. Another example is IEEE Dataport. This is source for data that's also curated. It's checked by people who work at IEEE. While, for example, something that's extremely popular for data sets, if you're looking for an open data set, is Kaggle. But Kaggle is something where anyone can upload anything here. Any data set, and a lot of data sets here might not necessarily be good. So usually, if you're checking a data set, you want to check which is the source of the data set. Has there been a publication related to it, etc., to make sure that this data set is good enough. For example, this is a decent data set. It has sources, it has examples of it being used. It's published by any university, a laboratory that deals with this. Yeah, but it requires some checking, and usually experts know which data sources are good or not, and where you can get actual okay sources automatically that will help you, get proper research, and you want to get your research turned down, because the worst thing that can happen to you is once you have completed everything, you developed your data-driven model, and now you're either publishing it or you are approving it for use somewhere, and people ask you, so where did you get your data? And you tell them, well, I found it online. And they tell you, oh, that's not good enough. We don't know if that data is valid. We don't know if that data, does it contain errors. We can't approve you just on, some data that was used somewhere. Or we can't accept your paper for publication, or we can give you a license to sell this software in medical fields or something else. So that's a big problem that happens, after you put in hundreds, thousands of hours of work in research once you get to that point. So that's something that can definitely be a big problem. One of the examples of this that I have is we wanted to do research on ship forms, basically vessels, how they influence the water resistance, etc. And we actually created research that allows you to generate using AI, optimize a ship form. But source for that, we found some data online, etc. And when we actually reached out to an expert in this field, colleague Darin Meinarich, who works in the Netherlands. He actually told us while doing that there are official sources, registries for ships that we can access, right? You can pay for access, and he actually had access because he works in that area. He had, himself as a person had private access to it uh, because he works as a consultant. And he said, I will just get you the data. Give me a few days to just download it, collect it, filter it, and I will send it to you. And without him, that research wouldn't have happened because we wouldn't know that that data existed, and we wouldn't. We would probably blow it off. We would say, "Oh no," because access to that sort of databases, private databases, is expensive, right? And I probably wouldn't spend a couple thousand euros for that type of research. But because we connected to an expert, not only was he able to tell us, hey, you can collect data here, but he was able to grant that access. And that's something that can happen often because, for example, I may not have access to a certain database that deals with physics data, but if I connect with someone who is a physicist, I can ask them, they might have access there uh, paid by their institution for research, and then we can join and work on research together, where they are basically providing and curating the data instead of me trying to collect the data from some weird source. Another thing is, I mentioned expert validation of the data. When we will talk later about tracking the data as it's collected and having an expert can help you immediately spot errors. I mentioned something like, temperature in the past, where you are measuring, you're measuring a temperature of something, and an expert can tell, oh, hey, there is a mistake here. This temperatures are showing very cold. It's probably an error with the temperature probe, maybe disconnected, maybe it fall off due to vibration or something. Let's check it immediately. And that's extremely, extremely helpful. Because, for example, if you're going to measure something, at a steam turbine, somewhere at a ship somewhere, and you're going there and you're attaching probes, you're measuring something for a couple of hours, you go back to your office, the ship leaves the port, goes to sail across the Atlantic, and you figure out that that one of the probes has fallen off due to vibration, or that there was a short circuit somewhere or something. You have lost that information, for it could be months until you can collect it again. And that's something that's key, having someone who can tell you right there that, hey, this data isn't necessarily fine. The data that we are collecting as we are collecting it is erroneous, right? And they are capable of doing that without checking the literature and analyzing, performing statistical analysis, because they are an expert in that field and they know it. They can, save you from essentially losing data. One of the examples here that I have is I essentially work with astronomers a lot. It's one of my passions in free time, and I combine it with my data science knowledge. And I was trying to collect data on an eclipse, measuring basically the eclipse timing and how the illumination changes thanks to it. And I had the camera that was misconfigured. One of the people who were there at this observatory that I was performing the experiment at, just glancing at my screen, was like, oh, okay, you have misconfigured, that shouldn't look like that. And they told me how to fix it immediately. So, we're talking about an event that happens once every couple of years. So collecting that type of data is something that I would need to wait to a couple of years to collect if I didn't have someone there who was able to tell me that I made a mistake, and I would realize I made a mistake only a few days later when I finally had time to analyze it. So that's what I'm talking about here. Whenever you're collecting data, especially data that's time sensitive that you can just collect tomorrow again, right? you want to have an expert sitting in with you and checking what you're doing. Contextual relevance is another thing because data isn't necessarily understandable to you. Basically, even if something looks, here's one example, something looks fine to you. Statistically, everything is fine. Again, we will talk about that. But they will tell you, hey, based on historical trends, like I know that the temperature here in, air temperature in Rijeka should be between 4 and 6 degrees Celsius right now. I'm seeing that the measurement is telling you minus 20 degrees. That's possible. It's physically possible for it to be minus 20 degrees here, but it's very unlikely. So can you please check your sensors to make sure everything is fine? That's sort of an example where actually, being placed into context, it can help you. If you're just collecting data for something that's not necessarily machine learning, where a model is going to act out something or make certain decisions. We're just collecting data to make certain decisions on its own without creating a model for it. You can do that without an expert who is going to tell you and actually, as it says here, give you actionable insight, tell you that, hey, this data here means that we need to do something. Like if you're measuring, for example, you're measuring how high a person's blood pressure is. For me, it's just a number, 130 over 85, okay. But a doctor is capable of looking at that and telling you, oh, that's fine, you don't need to do anything, that's great. Or they're capable of telling you, hey, your blood pressure is high, we need to run more tests and maybe give you certain pills to take, so we lower that, or you need to change your diet, etc. Basically, you need data without expert knowledge. Is just data, is just numbers, right? You need to have someone who's going to give you insight into it. The same is essentially, data interpretation, data analysis. You can do these things on your own. So this is less, okay, I can interpret patterns, I can, make inference, figure something out. This is something that we're already entering into area where you can use machine learning or computer vision or stuff like that to figure it out on your own. But you would be surprised how often experts can make a decision without AI being necessary. I reviewed a paper recently that was done by some researchers, and they were essentially they were measuring the pressure a foot makes while you are walking down the street. And they were trying to figure out is a person diabetic or not, because diabetes can affect a person's feet, right, negatively, and that could influence gait. And looking at the data that they were publishing, it was very obvious, right? They were just computer scientists. They didn't have a medical expert on field with them writing that paper. And because there was a medical expert, three of us reviewers basically told them the same thing. Hey, you haven't corrected for the fact that most people who have diabetes, one of the key symptoms of diabetes is being overweight. So we haven't accounted for that. And that's such a common comorbidity. So not everyone who has diabetes is overweight, and not everyone who is overweight has diabetes. But on your test data that you have, basically every person here that you have done measurements for is overweight. So that's why you get higher pressure. But you didn't take that into account. You have just measured the pressure, and that's why your research is essentially invalid. You haven't corrected for this. I promise you that if they had a doctor with them on that research, on that paper, doctor would be able to tell them that immediately, right? And they would have saved them a lot of time. And that's what I'm talking about, interpretation of data, because when the doctor would look at that, they would be able to interpret that data in its real light, saying like, oh no, this is just caused by people being, this is probably caused by people being overweight. Please, let's check the numbers. Oh yeah, that's something you don't need an AI model for that, and it's much faster to have an expert who can essentially save you a lot of time, right, by doing a basic, old school, uh, let's call it that way, data interpretation and analysis, where they can just scroll through the data, maybe run some simple correlation or trend analysis that you can do in your Excel, and interpret that, and go forward from that to basically tell you whether something makes sense or doesn't. And finally, is we're going to measure something that's called a bias. I think I already mentioned it. Basically, bias is tending towards something. When you have a bias in data, maybe you're collecting something inappropriately. For example, one of the examples, I'm going here with medical data. I'm using medical data a lot because I think it's close to everyone. If I talked about robotics or steam engines or steam turbines, and electrical power plants, it's not necessarily as close to everyone. So that's why I'm going with medical information here. So I hope you won't hold that against me. But basically, one of the biases is, for example, it can be age or it can be gender, and we are collecting. That's something that's pretty simple to check for, right? But sometimes, a lot of examples historically, one of the problems was that a lot of testing was done on men instead of women. Women weren't included in tests, and that introduced a lot of bias in research, especially testing for how well certain drugs perform, because not all drugs perform as well for people of different genders or different ages or different races, right? So that's something that isn't necessarily, especially historically, wasn't necessarily included. Uh, Especially one of the examples in drug testing is that usually you have people who are lower income who will go and do, and we're talking about extremely lower income. So we're talking people who are extremely financially disadvantaged, people who are homeless or nearly homeless, that will go and do this, drug testing, and their physiology is actually different because they live in different elements. If you are someone who can't afford to keep the heat on, and you are going to do drug testing because that's the only way you can hold food this month. You are probably going to be underfed. You're probably going to be at high risk of contracting a cold-related virus, etc. And there are a lot of, problems that this can cause, and it can negatively show up in the data. It can point to drugs being more effective or less effective than they actually are, because you haven't covered all the possible elements, right? When you were testing for example, drug performance on a certain group. So that's something that basically is something that experts, who have read papers in this area and who understand certain biases that exist, can help you understand that, hey, there is a problem. Another example is very simple. If you're driving a car and you want to collect data on how much gas the car uses when you're driving, it's not the same if you are driving it in city traffic or on highway, right? Because there are two different sets of usages, different types of usage, and your gas usage is going to be significantly different comparing highway to city. That's why you usually have two different numbers there, and that are the types of biases that you can introduce, and sometimes they're introduced negatively because people are trying to illustrate their point. So they will, take a car drive it around the city. That's just an example. Drive it around city, say, oh, this car spent, I don't know, 8 liters per kilometer, and they will take another car, drive it around highway for the same amount of kilometers, and they will say, well, on the same amount of kilometers, with the same average speed, etc., this car used less gas. It used only 6 liters. But the difference is that the way it was driven, how many accelerations and decelerations it had, etc. And that's the types of biases that can be introduced. Again, compliance with ethical standards is essentially something that each industry has. It exists. So basically, you can have different, ethical illustration standards in medicine. It's very important, for example, to have anonymized data, and that's something that differs from country to country, and there are examples where certain countries have laws that are more lax based on what data you can share and how. Some countries are more strict, and it depends on the type of data, the area that the data is in. So that is something that you as a computer researcher, a computer scientist may not know, but as an expert, you may be familiar that, hey, this type of data can be shared like this, etc. And finally, is we have to talk about what is the role of experts when it comes to data documentation, metadata, because data that when it's collected, we want to attach meaning to it through catalogizing it or storing it, attaching metadata, so additional information to it. Experts know what the data is important. For example, if we are taking a picture of something, it's very important to note what type of camera it was used and what were the settings, if settings are something that can be adjusted, ISO, exposure time, and blend aperture. Those are the things that can significantly influence the appearance of an image, right, of a picture that we've taken. But if they aren't noted, right, if you give me a DSLR and you let me take pictures, I will just set it to auto, and probably a couple of days later, if there is different lighting, I will get completely different, not completely different, but significantly different images. And if I have hired an expert, someone who isn't necessarily, a professional photographer, we aren't talking about that sort of an expert necessarily here, but just someone who has a know-how how to use that equipment, we can get much better, much more consistent data. Or even if the data is consistent, they will note that they have taken pictures with this exposure and this blend and this ISO. This time they will attach that information to the images, and if they take it in the next experiment, they take it with different data, right? With different metadata, with different information, they will note that. And a couple of months later or years later, when I'm looking at that data, I can compare metadata and be like, oh, that's why there is a difference here. It wasn't caused by some variable that I'm checking. It was actually caused by the change in metadata, right? But if both have this exact same metadata and all the metadata is filled properly, then I can make a conclusion. I can conclude that, hey, maybe there is an actual difference between these images based on something else, right? Some variable that I'm checking. And I mentioned this already, but basically, when it comes to real-time data collection, we want to have expert knowledge that they can tell us, basically identify an error or tell us what's the best way to collect data. Because when you are an expert in something, it's very probable that you have, especially if you are a professor at an university or something like that, compared to someone who is working in industry, right? We people in academia have much more time to check research, see what's being done, what other people are doing, what methodologies they are using compared to people who are in industry. So if you need to collect some data and you are unsure, if you reach out to someone at the university, they may be able to tell you like, oh, I've read this paper a couple of weeks ago where these people have been doing something similar to you. Let me show you the paper. Let me show you what they have actually been using and how they collected the data. And doing that, not only do you have advice on how to collect the data, but you actually have a reasoning on why you have selected that data. So if your boss asks you, so why are we doing this in this way? You can show them the paper and tell them, well, I asked this guy at the university, he told me this, he sent me this paper, these researchers from, I don't know, Oxford have done it in this way, so I think that's a good way to do it. So that's something that's super practical, basically to have that justification on how to do something. That's also something that I would, want to mention. Of course, there are things, for example, uncooperative data sources. We had a camera, high-speed camera in our laboratory that simply didn't work. It was broken. Oh my God, right? It's an expensive tool that isn't working. It wasn't. Basically, the person who uses that camera, right? When they came, they told us like, oh no, you just misconfigured it. Let's fix this, and now your camera is working. And that's something that can take you a lot of time to figure out. Basically, uncooperative data source simply means like my measuring equipment it's refusing to work with me. It's refusing to give me data. That's where an expert can just help you fix that. As I said, providing innovative solutions, because when you're more familiar, I mentioned as academics, we have much more time to sit back, read the paper. It's part of our job, and figure out how to address certain things. For example, missing data, as I said here, is an example that can be fixed, right, up to a certain point with certain techniques that the data can be filled, which is something that you may not know if you're just, someone whose job is to measure the data. Yeah, so that's something that experts can also help you with. And that follows here, effectiveness of data tools and technologies. This is mostly in terms of, helping you selecting the right software hardware. As I mentioned, we have expert might have more contact, just for example, if you're a computer scientist and or an engineer somewhere and you're designed to collect data and process data based on, in a certain industrial process. The person who is a mechanical engineer, right, who deals with that process daily, they may have been sent to trade shows or were shown presentations by people, who actually work in that area, who sell, and they may be more familiar with equipment that exists in that domain, right? So that's something that, again, experts can assist you with. Again, I mentioned about this is something that I mentioned before in big data, in a data storage and management class. Scaling data access can be a problem. If we are collecting data, it's not the same if we are collecting data from, for example, for patients from one hospital, or we are collecting it from 10 hospitals. This is a problem that we had, where we had like a pilot study at our local hospital, and then we were like, okay, everything is set up, everything is great. Let's involve 10 different hospitals in this, and everything fell apart because each hospital was doing something differently, right? And what we needed to do, we needed to sit down with these experts, right, from different hospitals, and go through everything with them and go through their specific data source. So the formats of images and metadata that they were sending us, because some people would include, a picture be a DICOM, and the DICOM format enables you to include metadata within the image itself. Okay. Others would send the DICOM image, but would use a PDF for metadata. The third hospital used text file for metadata with DICOM. Fourth hospital did not use DICOM, it used PNGs. So basically sitting down and making decisions, like for example, hey, can you send us DICOM instead of a PNG, because DICOM has higher bit depth, so it's better for us. And doing that, with different experts to allow us to scale this has allowed us to solve that problem. But it would have been much less stressful and much less problematic if we sat down in advance with these experts and discussed, hey, when I try to apply this piece of software to data coming from this other hospital, what are some types of problems that I could expect? If I reach out to those hospitals before, so hey, can you send me a sample of data to see if it works with our code? It would have helped me solve this problem. We didn't, and that caused issues, right? So that's something that an example of scaling where experts could help us. And just general, improvements on existing data collection methods. One of the biggest errors is setting down, creating, something that's a continuous data collection, like a protocol where, someone will send you data, or you set up a measuring device somewhere and you say, oh, it's going to be collecting data for years. I don't have to worry about it. Experts can tell you, basically, like if you're using a camera to record something continuously, 24 hours a day, you're trying to measure it, to collect data to do some analysis on it. Experts will be able to tell you when is the time to, hey, there are cameras, for example, thermal cameras that are much better than the one you're currently using. I know this because I go to trade shows. I get offers to purchase, scientific and engineering equipment like this because I'm an expert in thermal engineering. So I know that using this updating, it's worth it now to upgrade your equipment and to go through the effort of doing that. That's something that people can tell you, and that expert can tell you if it's time to upgrade equipment or the protocol you're using or data file formats that you're using right now or for future projects. Or they can tell you, no, like there are some new things, there are always new things, but they aren't really they don't improve so much that you need to go to the trouble of doing that. The old stuff that you're using is fine, right? That's something that can also be done, because again, there's cost involved with this, and the expert can tell you, like, oh no, these 10 thermal cameras are fine. You don't need to spend 100,000 euros on 10 new ones, right? So now I'm just going to give you a couple of examples of really significant issues that happened because, well, someone didn't talk to an expert. So the first example is you have probably heard about the term cold fusion. Just to give you, some background, if you go, when you do fusion with atoms, it produces energy, but produces a lot of heat, and it's not viable to use. If you can do that at room temperature, instead of pumping a lot of heat in the system, you could create a revolutionary source of energy, right? So here is, for example, in 1989, doctors Pons and Fleischmann believed that they have measured energy generation on a water cell right at room temperature. So they put a certain amount of electrical energy in, and they got more of it out. And based on their initial data, right, that they have measured and presented, one of their big errors was they actually published this data in newspapers, right, to journalists before they actually published it scientifically in a peer-reviewed journal. Basically, to those preliminary results, a liter of water, so salt water from the sea that you can, especially if you're from Croatia or Greece, you can just walk down, grab it. It will give you enough energy to keep your house running, your entire household running for 10 years, right? That's you can understand how significant that sort of discovery is. And here is that water cell that you can see. These are Dr. Spons and Fleischmann, right, who did this research from, and this picture is, if I'm not mistaken, from that infamous press conference, because before publishing the paper, they held a press conference, which is a big faux pas in scientific community. You get your research peer-reviewed first. And why do you get your research peer-reviewed first? Well, Pons and Fleischmann, Dr. Pons and Dr. Fleischmann were electrochemists. They aren't physicists. And while their experiment did work, well, it showed increase in temperature, which means increase in energy. They didn't figure out that there are other tests that need to be run. For example, this is running the experiment with heavy water instead of regular H2O, right? Is something that needed to be done, and that everyone else who was running these types of experiments, who was dealing with fusion, especially cold fusion, at the time was running, because it's important. I can't even explain to you why it's important. I'm not a physicist, right? But that's why it's important to have a physicist, because that's an example of something that they can tell you and give you, like, hey, you need to run this experiment in this manner as well. In the end, this was a very, very big thing. And there were actually people who recreated this tool and repeated their results. It's not really, like, physically it cannot exist in the way they have done it, right? And that's something that a physicist would have been able to tell them immediately, hey, you made a mistake. And it's what happened when the paper reached, the reviewers in the peer review process. It was turned down immediately. There was the way you're describing this, the data that you achieved is just simply physically impossible. And it's probably what probably happened. One of the greatest, one of the most assumed, things that this is the reason why there was this error is that they haven't properly grounded the temperature probe. So they haven't properly, made a connection between two wires, right? That's all. The people, doctors here, they have essentially ruined their careers over this. It was a whole, problem with this, entire. It was a massive scandal. There is a really great. I'm going to copy and paste basically let me just copy it. So there is a really great documentary freely available on YouTube based on this. It's in 3 parts. If anyone is interested, I'm going to share it here and just share it in the video. I'm going to say it's by Bobby Broccoli. It's 3 parts, and the first part is called The Dead Grad Student Problem. The dead grad student problem basically exists because it's called that because if there was cold fusion, the energy that actually would have released by the settings that Pons and Fleischmann provided, that someone should have died. The amount of energy would be expected so high that something should have exploded, and that was one of the errors, that there wasn't anyone injured in their experiments, pointed out that there was an error, right? And that's something that, especially if you're interested in this, you can watch it. It's almost 3 hours of. It's a really great documentary. So yeah, that's something that if they had a physicist with them, they would immediately tell them, no, this is wrong. You're getting some energy, but it's not enough. It's at the wrong spectrum. You're getting this energy from something else. You haven't grounded something properly. Your measuring device is broken. Something is wrong, right? And they would have avoided this big problem. A more recent example, couple of years back, from Korea, there were 3 scientists, Dr. Lee, Dr. Kim, and Dr. Kwon, who released a preprint. So that's basically just to clarify, you are scientists, so most of you probably don't know that when you write a scientific paper, what's the difference between a scientific paper and me writing something in newspapers. The scientific paper is sent usually anonymously to two or more, usually it's 4 or 5 reviewers who don't know, who I am, what I'm doing, and they will read the paper and check it to make sure it's fine. And if all of them, if just one of them usually says no, the paper isn't okay, like there is a methodological error, it's going to get refused. A preprint is something that when you send the paper, you can publish it, because that review process can take a couple of months, and sometimes people prefer publishing these preprints to basically show that they're working on something. So for example, if you have funding for this and you receive like, I don't know, 20,000 euros this year, but you need to publish a paper and you finish your research in November, you might want to publish a preprint so you can show like, hey, I did some work. It's currently in the process of being reviewed, but it's not, it's out of my hands. I'm waiting on the review now. So basically, just a side to explain to you why this being a preprint is what happened here, And they claimed that temperature exhibits superconductivity. That's also revolutionary, almost as revolutionary as this, right? 10 liters, because it means that right now when you want a superconductor, something that can conduct electricity without losses, you need to cool it, and you need to invest more energy than you save. But if you can do it at room temperature, that would, it's so revolutionary that you have no losses when you do any electricity transfer. Your batteries will last practically forever, because you can create superconductive batteries that don't have internal losses. It's amazing, right? And the reason why they figured this out, that this LK99, which they named, the material, is because when you put it on a magnet here, it levitates, right? As you can see, it's levitating. This is their videos of this that show it, actually levitating and fully, showing this example of levitation that is one of the indicators of superconductivity. But that's the problem, as I said, it's one of the examples of superconductivity, that's stable levitation. There are many, many more. For example, one of them is just measuring the resistance. If you have anything to do with electrical engineering or even computer engineering, you probably learned how to measure the resistance, and it's really, really simple. You take a tool that's called a multimeter or an ohmmeter with 2 probes, put it at 2 separate ends of wire, and you get its resistance. They didn't do that. Why? Because they are material scientists, and they never, they aren't electrical engineers. And because they didn't have, solid state physicists or electrical engineers who were able to tell them, hey, you just need to set up the experiment to measure resistivity, right? Resistance of that system, which is, as I said, banally simple. I can't explain to you how simple. It literally takes 3 seconds to measure a resistivity of a piece of material, right? Of course, the proper experiment to measure would require creating a wire and calculating stuff, etc. It would be more complex. But to just figure out that this isn't a superconductor, because it has a certain larger resistance, would take seconds. And they didn't do it because they simply didn't know, right? Yeah, so when the research was replicated, this LK99 material was remade at other researchers, at other laboratories. The simple, resistivity measurement showed that it's not superconductor. It just exhibits this stable levitation for some other reason that I want to go into here, right? So yeah, so that's an example, of something that was also very, very seemingly revolutionary. That not only was eliminated, but it was eliminated very, very simply, and of course, when this preprint came to publication, it was immediately turned down based on this reason. Okay, so these are some examples where these researchers could have saved themselves a lot of time because writing a paper and collecting the data on something isn't simple. It takes sometimes weeks, sometimes months to get everything properly done. So including an expert is super important in something like this, and you can misinterpret the data that you have based on you lacking the specific knowledge to run a certain experiment. Okay, so let's talk about tracking data. That's something that you will hear from when we're talking about data collection. We'll hear the term data tracking, and that's basically means that you want to, during the data collection, figure out an error. You don't want to, figure out that there is an error a few days later because, as I mentioned before, you can't always repeat that experiment. Sometimes, if you're in a laboratory, okay, great, you can do it. But sometimes you're conducting stuff outside of laboratories, you're measuring phenomena that's not repeatable, right? Because it's like an astronomical event or a weather event or something like that. And you can, or the experiment itself is very, very expensive, and you can't just be like, oh, I messed up. Let me spend, another $100,000 to run an experiment. Yeah. So basically, we will talk about tracking, the correctness of data as we are collecting it, and this usually means setting up. Uh, before I go, this means setting up a data stream, and automatically, for example, programmatically, I know you talk about Python. You can in Python, you have done some data visualization. You talked about it in previous classes. You can, automatically set up and measure certain things as you're collecting data. Automatically calculate certain items and figure out whether they are okay or not. And I'm going to talk about what are certain techniques and what are the indicators that will show you that you have miscollected data or something like that. So first is data distributions. How do you create calculated data distribution? You do this with something that's called a histogram. And it basically shows you, let me just change to this. You can basically create bins from this value to this value. I'm going to count the number of elements, and from this value to this value, this value to this value, each of these bins, I will count the number of elements. And when I get this distribution, that's how data is distributed. And it basically tells me that it's much more likely to get the data here instead of here, so what this tells me? It tells me, like, for example, that this data is distributed what we call normally. So we have a few examples, like, okay, I have this data here. I can see it's distributed smoothly, more or less. There are a couple of errors that I can get here. How can I detect this? So you will probably talk about this more in statistical analysis class that exists, but it essentially just tells us, like, hey, I'm more likely to get, if I randomly sample a data point, I'm more likely for it to be here than to be in this area. So one of the examples, this is normal distribution. Normal distribution is called normal because most elements in nature, when you collect the data on them, will have something like this. So for example, height of people, we will get most people around a certain height, and then you will have much less short people and less extremely tall people. And the more to the extreme you go, the less of them will be. So this is one very common distribution that you are going to look for when you're collecting data. And if you have missing value, right, for example, you can see, oh, okay, this fits the standard distribution here, it fits the standard distribution here. What happened here? Well, what happened here is that maybe you haven't collected the amount of data. Maybe there's a certain measurement error that your tool isn't measuring here. Maybe you have some sort of filtering setup that causes an error. And maybe this is something that's interesting. If all is correct with your data collection procedure, maybe this is something that you need to consult with an expert and see if, hey, maybe there's a phenomena here that we need to discuss and figure out. So that's something. So when we're talking about error here, it's not necessarily an error. It can be a great thing because you notice something that is unexpected, and you need to figure out what's causing it. And if you aren't what's causing it, your data collection procedure, it can be something interesting. But to do that, you need to eliminate and recheck your data collection procedure. So and again, as I said, showing more or less values in a certain bin can lead towards an error. Another error can be that different distribution than expected. So, for example, uh, an expert tells you like, hey, if we are measuring the height of people, we should get a normal distribution, something like this. We should get a lot of people here, in center. Most people should be, in our country around 170 centimeters, and going, taller or smaller, follow uh, they should follow normal distribution. Uh, and usually, a lot of research was done for different things, and people have probably measured whatever your field is, whatever area that you're in, they have measured something like this, and they figured out what is the proper distribution for it, because you can have something like a beta distribution, which is leaning more towards a side. You can have something like this, which is called the Weibull distribution, that is leaning, that's much more centered than normal distribution. You can have a normal distribution, but having it moved, it's not completely centered around some expected central value, but moved to the side. And all of this tell you something. So it can be perfect. So, for example, something like this, if you're talking about height, it can say like, oh, we are, people here tend towards shorter side, right? That's maybe something that it can tell you maybe there's a bias here. For example, one bias, if you get this sort of a measurement, maybe you need to check for height, maybe you need to check your age group, because maybe you are measuring a lot of children. So you are skewing to the lower end instead of being in the middle. Uh, that's some sort of an example, of something like this. If you're expecting a normal distribution, maybe you're for some reason measuring, you get less events in these areas that aren't near the middle. Why? Why is there this peak here? You need to sit down, usually with an expert, and figure out why is this here, unless you know that this is expected. Because in some cases, due to nature, you can expect, for example, this skewness. Because, for example, in developing countries where people may not have access to, healthy meals and food guaranteed, they may skew to, lower height, especially when they don't have, and don't have access to that as children, and they can grow to so. They can't grow properly. They may be skewing to the shorter side. Uh, so that's something that can sometimes be explained. It's not necessarily an error in your data collection, but something that has to be checked and noted and talked about. Uh, and it can basically, show an error of some sorts if it's skewed to one side or moved from the center where it should be. So that's something that can be discussed. So distributions are great. You can see them. You can see like, oh, this is skewing to this side. Yes, this is more centered than it should be. Maybe it should be very great, but that's complicated to do with a computer. Analyzing this curve is much more complex than analyzing a single number, and that's where descriptive statistics come in. First, it's much simpler to calculate them. We will see examples of this that I mentioned here: average, median deviation, kurtosis, skewness. They can be calculated relatively easily, especially with a computer. If you're using something like Python, you have built-in tools for calculating them. and you can monitor them much easily and automatically. You can just use, you don't need to measure different distribution here, calculate. That can take time. This is just a number that you're comparing to expected value, and if it runs out, if it grows past something, you just raise an alarm, right? And if you remember from data storage and management, when we talk about displaying, things for people to understand easily, giving us something like this, well, it can be hard to notice, if is this queuing to the side or isn't it? It seems maybe here, but I'm not sure. This example is like pretty clear to select. I selected them on purpose to be understandable, but it can be hard to understand. But if I have a value that turns a button that turns red, if I can just it turned red because there's something wrong with a value on my dashboard that I'm monitoring, and it's easier for me to figure that out. So that's why having a number is it's less descriptive than having something like this, because all of these values that you have here that we'll talk about are shown in this distribution, but they are easier to understand, especially for a computer if we're automating something. So average is something that we all know. We collect five different certain number of different values. We sum them together, so we have something like 5, 5, 5, 6, 4. We will get 25 divided by 5, and the average value of that will be 5. Okay, that's average. It's simple. It's good, and it doesn't give us a lot of information because you can get different. You can get the same average with a number of different examples. If we have a 4 plus 5, the average, if you have two elements, one is 4, one is 5, that's 4.5, okay, great. But and the average value is 4.5. But if you have 1 and an 8, the average value is again 4.5, but that's two very different sets. When you have, those are two very different sets of values, having a 1 and an 8 compared to having a 4 and a 5 in a data set. Like, these are, for example, we have your grades. If you have a 2 and a 5 and your average is 4, it's not the same as having a 1 and a 4 because you're failing, right? So, for example, we have some other values that help us. One is median, right? Median basically means that you have a data set, like you have a set that goes 5, 3, 1, 4. You sort that set and you get 1, 2, 3, 4, 5, right? And then you just look at the middle value in that set. So in this case, if you have 1, 2, 3, 4, 5, the median is 3. Why is that great? Because if there was an error here and we had something like minus 10,000, 2, 3, 4, 5, average will include that error, and it will tend greatly to that error. So if you have a data set that says 1, 3, 4, 5, the average value will be 3, right? As so in this example, in this first example, both where we have a set that is 1, 2, 3, 4, 5, so just 5 numbers in order, we're going to have the median and average be the same value. I'm writing in chat if you want to check that. But if you have a data set that we mismeasured something and the first value is minus 10,000, the second value is 2, then 3, then 4, then 5. The average of that is going to be the value of minus 1997.2, while the median will be the middle element when we sort it like this, which will be 3, right? Which will be the same value as it was before. And that's why both have a point in using them, but median generally better represents because it eliminates these extreme outliers, and we'll talk about outliers going forward a bit. But sometimes you want to include that outlier because you want to detect an error, and comparing median and average is a great way, just programmatically comparing these two values and seeing if they are similar can show you whether there is an error. Especially if there is a sudden change. And another example is standard deviation defined by this equation where you take the square value of so this is just divided by the number of elements. So for our example, it would be 5. Sum of the element minus its mean. So for example, to calculate the standard deviation, it will be a sum of all of our elements that we have here. So it will be 1 minus 3, because 3 is our mean value in this first data set. So we're talking about 1, 2, 3, 4, 5. Let me just open Notepad so I can show it to you on camera better. Okay, it's taking my computer some time to run the Notepad. Okay. So, we have 1, 2, 3, 4, 5 as our set. If we want to calculate the standard deviation, is going to be the mean value is going to be the average value is going to be 3. So we can just and so on. So we're going to have -2 plus -1 plus 1 plus 2. So that's going to be 0 when we end up, because we have a symmetrical data set. And we don't need to do the rest, of dividing, right? Because the standard deviation is 0. But if you have a data set that's something like this, we won't have that situation, because this first element will be minus 10,003. And let me just type it into the calculator. So it's so the first part is going to give us, the sum is minus 10,001. We will divide that by 5 because there are 5 elements. So that's going to be minus 2,000.2, and we are just going to need to square that. We are going to square the absolute value of 2,000 because we have a negative value, and that's going to be, a standard deviation of this set here is going to be 44. So we can see that we have a nice ordered data set. Its standard deviation is very low. If we don't have a nice data set, especially this value standard deviation needs to be checked in comparison with, average is going to be 3, median is 3, and standard deviation, usually shown as STD, is 0. So, this value of 0 compared to this isn't a big difference. It doesn't show a lot of variation. But if you have, a median of 3 and a standard deviation of 44 point something, that shows us 4.472. That shows us a significant deviation compared to our median, and that points to an error. That points to very big variance in our data, which isn't necessarily, sometimes we can expect a lot of variance in our data, but usually, depending on what we're measuring, it can point to an error, and we can detect that automatically. Finally, I talked about how skewed something is, how wide a data set is. That can also be expressed with two equations. They're a bit more complex this time, but again, you can see that this is very similar to, you have the elements minus the mean, and that's essentially what you're using to different powers, and it's going to define you how centered the dataset is. So this is an example of an extremely centered dataset. This is an example of a wide dataset. And skewness is going to show this is an example of unskewed dataset, right? This is a very skewed dataset, so it tends to one side, and this value tends, this is also skewed dataset, but much less than this one. So these values, again, you can approximate distribution with them, and you can do it programmatically. You get a number that's going to be, 0 if it's perfectly skewed, if it's not skewed at all, or tending to positive or negative value depending which direction is skewed. And if you're expecting something that's not skewed, if you're expecting a perfect normal distribution, you can automatically say, oh, I'm getting the skewness that's significantly growing to one side, and especially with that started happening suddenly, I can point out and say like, oh, maybe there is an error here, and I can automatically, detect that there's a change in the distribution compared to what's expected or to what was happening historically. That can point to an error, and that's something that when you are designing a data collection system, you can check. So when I'm talking about the data collection system, it can be something that's automated, and instead of just, most of my students, when I give them a task, collect data collection system, will just, connect a Raspberry Pi to a sensor and be like, oh, it's writing data to an SD card or sending it over the internet or whatever. That's the data collection system. No, the data collection system is something that not only collects data but checks its validity. And this is something that you can use to check the validity of data as you're going along. Because if you're collecting data that's, if you have data collection systems with low frequency, for example, when I sent you, at the start of the classes, I sent you one form to fill out, asking you to basically be like, hey, what's your knowledge in different areas connected to AI? That's something where I can, easily analyze using a distribution or something like that. I can point it out. I can draw it. I can see like how most people are around the median, or more people are tending to, having higher expertise, or more people are tending to lower expertise, because I have time, right? And because I have time to analyze that, and it's data that's collected at the start and never again. Like, I don't need to do it automatically. It's not something. But if I'm collecting, for example, data from an automated system, let me just share the presentation. The presentation was also sent to you, just pointing it out over the email, so you could have it there. There you go. I'm resharing the presentation for the people who just connected. Yeah, you can track it automatically, and figure out that there is an error if you're using a system that's, for example, I have a system that's measuring, because we have some earthquakes here, that's measuring, data automatically. And one way that I can figure out that an earthquake is happening is, in addition to my office shaking, is that it's going to check the values that it's collecting are going to be different. So it can automatically, without any further analysis, figure out that if the mean and the standard deviation of the values of the vibrations it's measuring are different, it can automatically figure out that an earthquake is happening. And this is something that a lot of people miss when you tell them like, oh, I want a data collection system, I want to design, or I'm designing a data collection system. It's not about just collecting the data, it's about processing the data, that initial data processing as well. And here are some examples of, distribution with low variance or high variance, with narrow or wide distribution. Again, this is, I say lower high is the value you're going to get from here. And same goes for high skewness, here is exponential, that's tending to one side. And something that's much lower, that's also skewed, but much lower, such as the beta distribution here. Okay, another thing that to cover here are, we have, just a few other things. We have outliers, right? So outliers are values that fall outside of a certain range, statistically speaking. So we are collecting data and we get a value, as I wrote before, we get a value like minus 10,000. That's outside of a certain range. And the problem with these outliers is that it can, so first of all, when we're talking about outliers, we usually talk about values that jump out in a way that's significantly different from the other values. So if we have 10,000 values that are around the average value of 5, in the range between 4 and 6, and you suddenly get a value that's 28, well, that's something that's not necessarily an error. Right? That's the difference between an outlier and an error. It can be, but it's something that's outside the norm, right? So, for example, if you're measuring, the height of people, I used that as an example before, and you get suddenly someone with, gigantism that's 2.5 meters tall, while everyone was around 170 centimeters before. That person isn't an error, it's obviously, but it's not useful to you when you're running a statistical analysis because that person is a special case. Same goes if you're measuring anything, you get spike. Sometimes the outliers are what you want to detect. For example, if you're looking for, you're developing a system that's detecting errors, where an error will very likely, depending on the error in the system, it might show as an outlier. But if you're building a system, especially you want to analyze something using a machine learning algorithm, you will very probably want to have a statistically data set that doesn't have outliers. Why? Because when you're running, your machine learning analysis, and you have an outlier, and you have your, something like you bring, an input, and your expected value is 5, and your model predicts 5 because that's what it has learned so far. It predicts, let's say 4.5. Then you have 4.8, and you predict, I don't know, 4.6. So you're making an error, but it's not significant. Then you get, I don't know, 5.9 as an expected value, and you get 4.9 as the value that your algorithm predicts. And suddenly you get an outlier, right? 1200. What happens now? Your algorithm isn't equipped to deal with this, very probably, if you're developing a machine learning algorithm, because most, 5,000 previous points were in this some range around 5. It's going to predict something in this range because that's what it learned. It learned that the values are around here. And it's going to predict something like, on the upper side of its range, like 6.1, but there is a significant error here. And if you analyze the performance of the algorithm, in reality, with these values, it's good. It's not a bad algorithm necessarily. But because you have this outlier that happened, that isn't, is a unique case, because you can develop an algorithm that will know everything and include every case. That's one of the problems with machine learning algorithms, is that they are sensitive to outliers and they're going to make errors for outliers. And that's why you usually want to sanitize the data and check for outliers first, even after you train your algorithms and you're exploiting it. You're running it as a program somewhere. You want to check whether an input might be an outlier. So that's something that you want to include, how to detect outliers. well, you're going to use something like this. So the first quartile, so if this is your entire data set, these are the values. The first quartile is the lower 25%, and each quartile is 25% of your data. So you have first, second, third, and fourth. The range between your first and your third quartile, if you're having normally distributed data, depending on its quartiles, is how wide it is, it's going to collect around 50%, and that's what you're expecting to have here. And that range will, based on that standard deviation that we calculated, is going to be between 0.6754 positive and negative standard deviation, and that's where 50% of your data will fall in. The rest of your data is going to fall in between first quarter minus 1.5 times this interquartile range. So we're expanding this to here and here, and that's going to be around 2.698 minus 2.698 and plus 2.698 standard deviations. These are some approximate values, this formula. So the value at the edge of the first quartile minus 1.5 times IQR, or value at the start of the third quartile plus 1 times IQR into this range of values is going anything outside of those ranges, we will say it falls out. It's an outlier. It's not the value that should be here. And in graphs, they will usually be indicated with circle outside. If you ever see this graph, this is the interquartile range, the error based on the standard deviation. This is the actual range, of the variables. This is the median value of the variables in the data set, and the points that may be shown here are outliers, right? So just helping you read data. And when you do something like this value, Q1 minus Q3 plus, is something that you can calculate programmatically and automatically eliminate those outliers. When I say eliminate, let me just clarify, because I used the term a couple of times. You usually want to save, if you're pre-processing data in any way, you usually want to save raw data, because outliers might not be important to you now. You want to eliminate them, but maybe they are useful for other analysis in the future. So why repeat the data analysis process? Instead, just save two data sets. Save the data set with outliers and without outliers. That's just an advice here. And the final thing here we have is out of range values. That basically outliers are statistical. There, as I mentioned, outliers aren't errors. Outliers can be something that's for example, I'm very overweight, so if you measure my weight, I'm probably going to be somewhere around here. But if you're very short, you may be somewhere around here. You're not an error. You are just, outside of the normal range. That's what outliers are. Out of range values are values that are out of actual expected possible range of values that you can expect or that you can measure. We are usually talking about what you can measure, because you don't want to make assumptions about stuff that you're measuring. But you have to, because your equipment will have a range that you can measure in. If you are measuring, as I said, someone's height, you will have a stick or a meter that goes up to, I don't know, 2 meters. And if someone that's 2.1 meters tall comes in, well, your stick is probably too short. You probably want to have a longer stick. But if you have a 5-meter stick and someone comes out, well, that's probably an error. So in general, you want to know we are talking about values that are outside of a range that your equipment has. And there are two values to discuss here. First is the possible range that can measure, and a reliable range. And this is usually values, especially when you're buying, high quality equipment. They will tell you, hey, we can measure between minus temperature between minus 70 and plus 80 Celsius in the room. But our error here isn't that low. We can measure it. It won't break, but it's not precise. And our reliable range is between minus 20 and plus 40 degrees Celsius. So that's and usually when you're measuring stuff, you want to use the equipment's reliable range. If you get out of range values out of reliable range, you can sometimes, if you want to be very precise, discard them, or you can get values that are outside of possible range as well. Those are error values that you have to detect and figure out that you get an OOR or out of range error. So this is what I'm talking about. That's an out of range error. Some measuring equipment will figure this out immediately and show it to you. For example, I mentioned ohmmeters or multimeters, digital multimeters. When you get out of range, if you're trying to measure resistance and you're in a range of 1 kilo ohm, you can plug it in and it will show you just one, right? One indicates that it's out of range. That's very common in multimeters for electrical engineers. One of the famous examples of these out of range values is the so-called, I noted it here, possibly apocryphal. I have actually seen a documentary that says that yes, this was actually true, so we can ignore this apocryphal element. But basically, story is that after Chernobyl catastrophe, they measured, the people who were working there measured the radiation value of 3.6 Röntgen, and this value is high, but it's not alarming. There is a quote from a show, drama part documentary show about Chernobyl, where the lead engineer says that 3.6 is not great, but it's not terrible. It's not a massive problem. The problem actually is that the equipment, the measuring devices they had there, this is the highest possible value it could measure, and the actual measurement was much higher. And because the equipment showed 3.6 Röntgen, they have assumed that the core did not fail, and that everything is fine. Okay, there was an explosion, there was a problem, but it's not such an alarming situation. It's something that can be resolved instead of properly panicking as they should have at the time. So that is something that is a historical example of an out of range error, and it can happen to you because a lot of equipment will default to its maximum or minimum possible range when you're measuring, especially analog equipment. And another problem with out of range is that, especially with analog equipment, you can break it. If you connect to a multimeter too high of a value, you can actually break the equipment and damage your measuring devices. So how do you do this? Well, the best way is know what is the actual possible range. Once you know the actual possible range, like even crazily high, you can get. One example is like, okay, I want to measure, for example, we have 3.6 Röntgen. I want to be precise in measuring stuff between between zero, no radiation, and 3.6 Röntgen. Great. But you may want to get additional equipment that measures high. It might not be as precise, but it has a wider range, so you can detect out of range errors. Right? If you don't have funding to get, because the wider, in most cases, bigger range with the same precision will be much more expensive, like exponentially more expensive than getting equipment that's precise in a smaller range. But you can get cheaper, less precise equipment as just monitoring equipment if you're expecting a lot of out of range errors. And you can use this equipment. It can commonly be used to just raise an alarm, like, hey, I don't know if the temperature here is exactly 63 degrees, but I know it's above 50 degrees and people shouldn't be in here. Let's evacuate everyone outside. So that's something that can be, instead of we're getting a very precise measurement, but with a thermometer that doesn't go above 40 degrees, and the temperature in the room, in a storage facility or something is 55 degrees, but your thermometers are turning 40 because it's the top of its range, right? So those are out of range errors, and again, they can be extremely dangerous. not just as a mismeasurement, but they can actually damage your equipment or cause human suffering due to mismanagement. So that's something that you need to be very, very careful about. Again, how will you know what is the upper range? Check the literature, consult with experts. Okay. So that's it for today. We are going forward, we're going to discuss other topics such as data redundancy, etc. I believe we have 3 lectures in total. Yes. So the next one is on 13th. That's Friday, and the last one is just going to be showing some examples, etc. On the 18th. So yeah. So that's it for today. Uh, Again, if you have any questions, you can type them in the chat. Ask me. If not, I'm going to finish for today. Okay, so I see. Okay, so it's just thank you. No one else is typing anything. So that's it. You should have received an email from me today. So we can just reply to that if you have any questions or anything. And I will upload this lecture today on YouTube. So let me just the Erasmus Plus WICT YouTube. It We had some issues with people accessing accessing it, so it's currently for the duration of this class we are going to keep it fully open, so you don't need so I don't need to send you individual links or anything. So it's going to be, it's not the playlist isn't here yet, but it's going to be added soon after I process this video and upload it, so in a few hours. Okay, so that's everything. Again, if you have any questions, email me, and if not, thank you very much for your attention, and goodbye.
Goodbye.
Thank you very much. Goodbye.